At 4:30 UTC on February 24th, 2022, approximately 90 minutes before the Russian ground invasion of Ukraine began, an attacker logged into a management server operated by Skylogic, a subsidiary of the satellite operator Viasat. The server was located in Turin, Italy. The attacker used administrative credentials that have never been publicly explained, although the US Cyber Command later attributed the operation to the Russian GRU's Unit 74455, also known as Sandworm. From the Turin server, the attacker pushed a custom firmware update to approximately 40,000 satellite modems across Central and Eastern Europe. The firmware contained a wiper component called AcidRain, which overwrote the modem's flash memory with random data, rendering the device permanently inoperable. The attack propagated through the Viasat KA-SAT network for several hours, disabling terminals across France, Germany, Italy, Hungary, Poland, and Ukraine, including approximately 5,800 wind turbines in Germany that depended on satellite connectivity for remote monitoring, and approximately 30,000 commercial users across multiple countries. The Ukrainian military's reliance on Viasat for command and control of frontline units became operationally significant within the first hours of the war. The Russian electronic warfare units accompanying the invasion had specifically prepared to jam terrestrial radio communications on the assumption that satellite connectivity had already been disabled by the AcidRain operation. This assumption was correct for the first 72 hours. By March 1st, the Ukrainian Vice Prime Minister Mikhailo Fedorov had publicly requested Starlink terminals from Elon Musk on Twitter. By March 28th, approximately 5,000 terminals were operational in Ukraine. By June 2022, the number exceeded 15,000. By 2024, approximately 47,000 terminals were operational across Ukrainian military and civilian use. The Russian Ministry of Defense allocated specific units and significant resources to disabling the Starlink service in Ukraine through 2022, 2023, and 2024. The operations included radio frequency jamming using Terrata 2 and Bylina MM systems, cyber operations targeting the terminal firmware, and at least 2 attempted operations to physically capture terminals for reverse engineering. None of these operations achieved the Viasat equivalent outcome of disabling the system across the theater. The reasons are technical, and they will be explained in this video. Understanding why one satellite internet system collapsed in hours, while another survived 3 years of sustained nation-state attack, requires understanding how these systems actually work at a level of engineering specificity that popular coverage of the industry rarely reaches. That is what this video is about. Satellite internet exists in 3 generations operating simultaneously, distinguished primarily by orbital altitude. This is the central engineering fact of the industry, and treating all satellite internet as a single category is the most common mistake in popular coverage. The geostationary generation, including Viasat, HughesNet, and the Inmarsat constellation, operates at 35,786 kilometers above the equator. Round-trip latency is 600 to 800 milliseconds. The architecture is centralized around a small number of large satellites. The medium Earth orbit generation, exemplified by SES's O-3b at 8,063 kilometers, achieves 150 millisecond latency. The low Earth orbit generation, including Starlink at 550 kilometers and Kuiper at 590 to 630 kilometers, achieves 20 to 40 millisecond latency, comparable to terrestrial cable. The trade-off that determines everything else is geometric. A geostationary satellite covers 1/3 of the Earth. A low Earth orbit satellite covers a circle approximately 1,000 kilometers in radius and moves across the sky at 27,000 kilometers per hour, remaining visible from any given ground point for approximately 4 minutes. To provide continuous service from low Earth orbit, the constellation must be large enough that as one satellite disappears over the horizon, another is rising. This requires thousands of satellites in coordinated orbital planes. The user terminal connects through a phased array antenna that electronically steers its sensitivity to track moving satellites without physically moving. The Starlink terminal contains approximately 1,280 antenna elements. The handoff between satellites occurs every 2 to 4 minutes, invisible to the user. This is the standard technical context. The remainder of this video addresses material that the standard treatment does not contain. The Russian electronic warfare campaign against Starlink in Ukraine is the most extensively documented sustained attack on a satellite internet system in history. The public record drawn from Ukrainian military disclosures, defense industry analysis, and statements from SpaceX engineers allows for a more specific technical account than has been widely presented. The jamming campaign, Russian forces deployed the Tarata-2 satellite communications jammer at multiple locations across occupied Ukraine beginning in spring 2022. The Tarata-2 is designed to disrupt satellite communications by transmitting high-power radio frequency noise across the bands used by commercial satellite systems. The initial operations targeted the Q-band downlinks used by Starlink terminals, attempting to overwhelm the legitimate signal from the satellite with locally generated noise. The first response from SpaceX was a software update pushed to terminals in the affected regions within days of the jamming being identified. The update modified the signal processing in the user terminals to discriminate more aggressively against signals not originating from the expected satellite direction. Because the Starlink terminal already knows the precise location of the satellite it is communicating with at any given moment. Signals arriving from other directions can be filtered out at the signal processing level. The phased array antenna's electronic beam steering capability, originally designed for tracking satellite handoffs, was repurposed for active jamming rejection. The second response, deployed in late 2022 and early 2023, involved frequency hopping. The Starlink protocol was modified to rapidly shift the specific frequencies used within the Q-band, faster than the Russian jammers could follow. The modification was deployed entirely through software updates to the existing terminals and satellites, with no hardware changes required. The third response, deployed through 2023, involved adaptive power management. The satellites began transmitting at higher power levels in regions where jamming was detected, while reducing power in regions where it was not. The trade-off is total constellation capacity, because higher power transmissions consume more of the satellite's power budget and reduce the bandwidth available for other users. SpaceX accepted this trade-off as part of the operational commitment to maintain service in Ukraine. The Russian counter-response deployed in 2023 was the Tobol electronic warfare system, which is more sophisticated than the Tarata-2 and is designed specifically to disrupt satellite navigation and communications by transmitting interference signals from the satellite's perspective rather than the ground's. The Tobol attempts to inject signals that the satellite interprets as legitimate uplink communications from authorized terminals, potentially confusing the satellite's allocation of resources. The SpaceX response involved cryptographic verification of terminal identity at the satellite level, with rejection of signals that fail the verification regardless of their apparent origin. This is the engineering pattern that defines the Ukrainian campaign. Russian electronic warfare units identify a vulnerability, attempt to exploit it, and SpaceX engineers deploy a software countermeasure within days or weeks. The countermeasures are possible because the constellation was designed from the beginning to be reconfigurable in software at the protocol level, not merely at the application level. This is a deeper form of software-defined architecture than most networks possess. The cyber campaign. Parallel to the jamming operations, Russian cyber units attempted to compromise Starlink terminals directly. The most significant publicly documented operation occurred in summer 2022, when terminals captured from Ukrainian positions were sent to Russian laboratories for reverse engineering. Researchers at Belgian and German universities had previously published academic work demonstrating that the Starlink terminal could be modified to extract its software, which the Russian effort attempted to replicate at scale. The SpaceX response was to push firmware updates that detected the specific modifications used in the academic work and rendered modified terminals inoperable. The mechanism is similar to what is used in console gaming systems to prevent piracy. The terminal performs continuous self-verification of its hardware state and shuts down if tampering is detected. This produced an operational asymmetry. Russian forces capturing Starlink terminals from battlefield positions could not effectively use them because the terminals would either be remotely disabled by SpaceX once the change in location was detected, or would self-disable if modifications were attempted. Multiple operations to deploy captured terminals for Russian military use were documented as failed through 2023. The physical campaign. Russian forces attempted to physically locate user terminals through direction-finding equipment that detects the radio emissions from the terminal during operation. The Starlink terminal transmits at relatively low power on a narrow beam, directed precisely at the satellite, which makes it difficult to detect from positions not aligned with the satellite direction. However, the terminal is not invisible. Russian forces successfully located and destroyed numerous Ukrainian terminals through artillery and drone strikes guided by direction-finding equipment. The Ukrainian operational response was to deploy terminals in dispersed configurations, with frequent relocations and the use of decoy terminals to confuse direction finding. This is a tactical adaptation rather than a technical one, but it is significant because it demonstrates that the system's resilience is not purely a function of the technology. The technology provides the foundation, but operational tactics determine how effectively the foundation is exploited. The cumulative result of 3 years of sustained nation-state attack is that Starlink service in Ukraine has degraded measurably during specific operations, but has not failed at the system level. Individual terminals have been destroyed. Specific regions have experienced temporary outages. The system as a whole has continued to function. This is the empirical demonstration of the architectural arguments that the next section will explain. The Viasat KA-SAT system that AcidRain disabled in February 2022 was designed in the mid-2000s and launched in 2010. The Starlink system was designed beginning in 2015, with first operational launches in 2019. The decade and a half between them encompassed the period in which nation-state cyber operations against civilian infrastructure transitioned from theoretical concern to operational reality. The architectural differences between the two systems reflect that transition. The terminal management plane, the Viasat KA-SAT, terminals were managed through a centralized server infrastructure with administrative access protected primarily by credential-based authentication. Once an attacker obtained valid credentials, the system did not enforce additional verification before accepting firmware update commands. This is the specific vulnerability that AcidRain exploited. The Starlink terminal management plane uses cryptographic signing of all firmware updates with hardware-rooted keys that cannot be extracted from the secure enclave on each terminal. An attacker who compromises SpaceX's management infrastructure would still be unable to push malicious firmware to terminals because the terminals will reject any firmware not signed by the correct hardware keys. The signing keys are stored in hardware security modules with strict physical and procedural controls. The architecture assumes that the management plane will be compromised at some point and is designed to fail safely when that occurs. This is the most significant single architectural difference, and it is invisible from the user's perspective. It exists entirely in the firmware verification and key management infrastructure. It would not have been a standard design choice in 2010. It became a standard design choice for security-critical infrastructure by 2015. The Viasat system reflected the threat model of its design era. The Starlink system reflected the threat model of its design era. The signal-level vulnerabilities. Geostationary satellite internet at the Ka-band, which Viasat used, has specific signal-level vulnerabilities that low Earth orbit Q-band systems do not share. The Ka-band uses narrower spectrum allocations than Q-band, which makes jamming more effective with a given amount of jammer power because the jammer can concentrate its emissions across the entire used spectrum. The geostationary architecture means the satellite is at a fixed position in the sky, which makes directional jamming straightforward because the jammer can be oriented to point precisely at the satellite from the ground. The single satellite per region architecture means that disrupting communications with that satellite disrupts all service in the region. Low Earth orbit Ku-band systems with constellation architecture present the inverse profile across all three dimensions. Wider spectrum allocations dilute jamming power. Moving satellites make directional jamming require continuous re-aiming at hundreds of targets across the sky. Multiple satellites visible from any given region means that disrupting any individual satellite affects service marginally rather than completely. The Russian electronic warfare doctrine developed against geostationary satellite systems through the 2000s and 2010s does not transfer effectively to the low Earth orbit architecture. This is not because the Russian capability is technically inadequate. It is because the architecture itself presents a different problem that requires different countermeasures, and the development of those countermeasures requires time. The Russian forces did not have between February 2022 and the operational deployment of Starlink in Ukraine the following month. The orbital diversity advantage. The Starlink constellation includes satellites in multiple orbital shells at different altitudes and inclinations. A user terminal in Ukraine at approximately 50 degrees north latitude is typically able to see 15 to 25 satellites simultaneously across the 53-degree inclination shell, the 70-degree inclination shell, and the polar shell at 97.6 degrees. The terminal selects the satellite with the best signal characteristics, but it could select any of the available alternatives if the current selection becomes unavailable due to jamming, atmospheric conditions, or satellite failure. This produces an operational property that has no equivalent in geostationary systems. The constellation degrades gracefully under attack. Loss of any individual satellite or jamming of any individual orbital path reduces capacity rather than eliminating it. The system continues to function with reduced performance across essentially any partial attack scenario. To produce complete service denial, an attacker would need to either compromise the constellation at the protocol level, which the cryptographic architecture prevents, or physically destroy satellites at a rate exceeding their replacement, which would require capabilities that no nation currently demonstrates publicly and would generate orbital debris at levels that would affect all users of low Earth orbit, including the attacker's own assets. The combination of cryptographic firmware verification, signal level diversity, and orbital diversity produces a system that is not invulnerable, but is structurally resistant to the categories of attack that disabled Viasat. The resistance is not incidental. It is the result of specific engineering decisions made by people who anticipated the threat environment that subsequently emerged. The high-frequency trading industry's interest in satellite internet is the most economically significant commercial application of low Earth orbit constellations that popular coverage rarely addresses with specific numbers. The mathematics that justifies the infrastructure investment is worth examining directly. The current fastest terrestrial connection between the New York and London financial centers is the Hibernia Express transatlantic fiber optic cable, completed in 2015 at a cost of approximately $300 million. The cable was built specifically for high-frequency trading customers, with a route optimized to minimize total length rather than to follow existing infrastructure corridors. The round-trip latency from the New York Stock Exchange to the London Stock Exchange via Hibernia Express is approximately 58.95 milliseconds. The theoretical minimum latency for the same route through a low Earth orbit constellation with optical intersatellite links is approximately 43 milliseconds. The gain comes from two sources. First, the Great Circle distance between New York and London is approximately 5,585 kilometers, but the actual cable route is closer to 6,000 kilometers due to landing point constraints. Second, the speed of light in a vacuum is 299,792 kilometers per second, while the speed of light in optical fiber is approximately 204,000 kilometers per second due to the refractive index of glass. The combined effect is that a signal routed through space at the Great Circle distance arrives approximately 16 milliseconds faster than a signal routed through fiber at the actual cable distance. For high-frequency trading, 16 milliseconds is an enormous advantage. The pricing of certain derivative instruments depends on the relationship between underlying securities traded in different markets, and the firm that can identify and act on price discrepancies first captures the arbitrage. The annual revenue of the high-frequency trading industry attributable to transatlantic latency, arbitrage is estimated at between $100 million and $500 million, depending on market conditions. A firm that can reduce its transatlantic latency from 59 milliseconds to 43 milliseconds captures a disproportionate share of that revenue. This is why companies including McKay Brothers, which operates microwave networks for high-frequency trading, and several less publicly named firms have signed contracts with satellite operators for dedicated capacity. Starlink does not currently offer the deterministic latency guarantees that high-frequency trading requires, because the constellation routing is optimized for general consumer service rather than for predictable transit time. The high-frequency trading customers are paying for the development of a separate service tier with dedicated routing and latency guarantees, which Starlink has confirmed is in development. The implications extend beyond high-frequency trading. Any application where the speed of information determines economic value, including foreign exchange trading, commodity trading, and certain categories of cybersecurity response, has the same physical advantage available through satellite routing. The first generation of these services is launching in 2026 and 2027. The competitive structure that results is significant. The transatlantic fiber optic cable industry has invested approximately $3 billion in current generation infrastructure that is now technically obsolete for the highest value use cases. The cables remain economically essential for general internet traffic, where bulk capacity matters more than latency. But the highest margin customers, the ones whose willingness to pay funded the latency optimized cables in the first place, are now reachable through a different infrastructure that did not exist when those cables were planned. This is the first time in the history of the internet that the fundamental physical limit of fiber optic transmission has been exceeded by an alternative architecture at commercially relevant scale. The long-term consequences for transatlantic and trans-Pacific data infrastructure investment are still being worked out by the financial actors involved. The Starlink constellation includes approximately 7,000 operational satellites. The total population of active satellites in low Earth orbit across all operators exceeds 11,000. The total population of tracked objects larger than 10 centimeters in low Earth orbit, including debris from previous collisions and end-of-life satellites that have not yet re-entered, exceeds 35,000. The risk that any two of these objects will collide on any given orbit is small in absolute terms, but cumulative across the constellation lifetime in a way that requires active management. The Starlink satellites each contain an autonomous collision avoidance system that performs continuous risk assessment against a database of all tracked objects in the relevant orbital range. The U.S. Space Force's 18th Space Defense Squadron publishes orbital tracking data through the Space Track service, which the Starlink satellites use as their primary information source. When the predicted probability of collision with any tracked object exceeds approximately 1 in 100,000, the satellite autonomously executes a maneuver to adjust its orbit and avoid the conjunction. The frequency of these maneuvers is the indicator of constellation density that has not been widely reported. SpaceX disclosed in a 2023 FCC filing that Starlink satellites collectively executed approximately 25,000 collision avoidance maneuvers in the 6 months ending November 30th, 2022. By the equivalent period in 2024, the number had approximately doubled. The growth tracks the constellation expansion. By the time the planned Starlink, Kuiper, Guowang, and Qianfan constellations are fully deployed, the maneuver rate across the combined constellation will likely exceed 1 million annually. Each maneuver consumes a small amount of the satellite's onboard propellant, which is provisioned for the planned 5-year mission duration. The constellation is designed assuming a certain budget of avoidance maneuvers across the mission. Exceeding that budget shortens the mission duration, which requires earlier replacement and accelerates the cycle of launches and deorbits. The orbital debris environment becomes a direct operational cost. The risk that the system is designed to avoid is the Kessler syndrome, in which a single collision generates debris that triggers additional collisions which generate more debris in a cascade that eventually renders the affected orbital altitude unusable for any spacecraft. The 2009 collision between an inactive Russian Cosmos satellite and an active Iridium satellite generated approximately 2,000 trackable debris pieces and an unknown larger number of smaller fragments. A collision involving a modern Starlink satellite would generate substantially more debris due to the satellite's larger size. The probability of a constellation-scale Kessler event is low under current operational conditions, primarily because the operators are coordinating actively to prevent it. The probability under conditions of armed conflict involving anti-satellite weapons is significantly higher. The 2007 Chinese anti-satellite test against the Fengyun 1C satellite generated approximately 3,500 trackable debris pieces, some of which remain in orbit and require avoidance maneuvers by Starlink satellites today, 18 years after the original event. A handful of such tests, or a single deliberate cascade event by an actor seeking to deny low Earth orbit to all users, would have consequences measured in decades. This is the strategic vulnerability that the constellation architecture does not solve. The system is resilient against attacks targeting it specifically. It is not resilient against attacks that destroy the orbital environment in which it operates. The atmospheric consequences of satellite re-entry are the least covered significant aspect of the constellation industry. The specific chemistry and the specific numbers have been published in peer-reviewed work, but have not entered popular coverage. A Starlink satellite at end of life is deorbited and burns up in the upper atmosphere at altitudes between approximately 60 and 80 kilometers. The satellite's structural materials, primarily aluminum alloys, are oxidized at the temperatures generated by atmospheric friction. The resulting aluminum oxide is deposited as small particles in the stratosphere and mesosphere, where it remains for years before settling to lower altitudes. A 2023 study published in PNAS by Daniel Murphy and colleagues at the NOAA Chemical Sciences Laboratory measured the existing concentration of satellite-derived metals in stratospheric aerosols using high-altitude aircraft sampling. The measurements found that approximately 10% of the sulfuric acid particles in the stratosphere already contain aluminum, lithium, copper, and lead from satellite re-entry. This was before the major constellation deployments had reached full operational scale. A follow-up modeling study published in 2024 by Jose Ferreira and colleagues at the University of Southern California projected that the deployment of currently planned constellations will inject approximately 360 metric tons of aluminum oxide into the stratosphere annually by 2030. This compares to approximately 16 metric tons annually from natural meteoric input. The constellation industry will become the dominant source of metallic aerosols in the upper atmosphere within the current decade. The atmospheric chemistry consequences are not fully understood. Aluminum oxide particles in the stratosphere catalyze chlorine-mediated ozone destruction through reactions similar to those that occur on polar stratospheric cloud particles. The Montreal Protocol's success in reducing stratospheric chlorine through the phase-out of chlorofluorocarbons assumed a particular surface area of catalytic particles available for the relevant reactions. Significantly increasing that surface area through aluminum oxide deposition could partially offset the ozone recovery that the protocol has achieved. The 2024 USC modeling study estimated that the projected aluminum oxide injection could delay full ozone layer recovery by years to decades, depending on assumptions about particle size distribution and atmospheric circulation. The uncertainty range is wide because the relevant chemistry has not been studied at the concentrations that will exist by 2030. There has been no equivalent atmospheric condition in human history to calibrate the models against. The second consequence is stratospheric aerosol radiative effect. Particles in the stratosphere reflect solar radiation, producing a cooling effect at the surface. Volcanic eruptions that inject sulfur into the stratosphere cause measurable global cooling for 1 to 3 years after the eruption. The projected aluminum oxide injection from satellite reentries is small compared to a major volcanic eruption, but it is continuous rather than episodic. The cumulative radiative effect over decades is not currently included in climate models. The regulatory framework for these consequences does not exist. The Federal Communications Commission, which licenses satellite constellations in the United States, evaluates orbital debris risk, but does not evaluate atmospheric chemistry impacts. The Environmental Protection Agency, which regulates air pollution, does not have jurisdiction over emissions that occur at altitudes above the troposphere. The International Telecommunication Union, which coordinates global spectrum allocation, has no environmental mandate. The constellation operators are not currently required to account for atmospheric consequences in their business planning, and the science to require accounting did not exist until 2023. This is the consequence of the architecture that the industry will be forced to address in the second half of the decade by mechanisms that have not yet been designed. The discussion has not occurred publicly because the technical community working on it is small and the popular awareness is minimal. Within 5 years, this will be a primary regulatory question for the industry, and the actors who position early will determine how the question is resolved. This video has covered material that the dominant existing treatments of satellite internet do not address. The specific operational details of the AcidRain attack on Viasat in February 2022, drawn from the US Cyber Command Attribution and subsequent technical analysis. The specific Russian electronic warfare systems deployed against Starlink in Ukraine, and the specific software countermeasures SpaceX deployed in response. The cryptographic firmware verification architecture that prevents an AcidRain equivalent attack on Starlink at the protocol level. The latency arbitrage mathematics that make low Earth orbit constellations financially relevant to the high-frequency trading industry. The collision avoidance maneuver rates that indicate constellation density approaching the operational limits of low Earth orbit. The specific atmospheric chemistry of satellite re-entry, and the regulatory gap that will become a primary industry question within 5 years. These are the topics that determine the strategic shape of the industry in the second half of the decade. They are not the topics that competitor coverage emphasizes. The reason is partly that they require synthesis across defense industry analysis, financial industry economics, space situational awareness data, and atmospheric chemistry, which are domains with limited overlap in the technology journalism profession. They are also topics where the public record has expanded significantly in the past 18 months, and analysis based on that expanded record has not yet propagated through popular coverage. The strategic position of the satellite internet industry in 2026 is determined by the operational record from Ukraine, by the financial industry use cases that are now reaching commercial deployment, by the orbital debris environment that increasingly constrains operational decisions, and by the atmospheric consequences that will increasingly constrain regulatory frameworks. Each of these factors will become more visible to popular coverage over the next several years. The viewers of this video are seeing them earlier than the median observer, which is the point of analytical content that targets information gain rather than information confirmation. The next video in this series will examine the Taiwanese Sovereign Constellation Project, the specific technical and operational decisions being made by the Taiwanese government to deploy a satellite internet capability that does not depend on Starlink or any other non-Taiwanese system, and what those decisions reveal about how the sovereign constellation generation will differ architecturally from the commercial generation that preceded it. Subscribe to be there when it lands.